Assalamualaikum and hi, I am Dr. Noridah Osman, a Senior Lecturer in Chemical Engineering Department and Center in Biofuel and Biochemical Research at University Technology Petronas. Today, I would like to present my innovation on drop-type fixed bed reactor. This product was inspired to solve industrial problem where ton and ton of biomass waste are produced annually and currently underutilized for its contents. This biomass waste have a lot of valuable chemical within its structure, so by utilizing all this unwanted material, we can create new organic substance without producing any additional waste. Why we choose pyrolysis? We choose pyrolysis because pyrolysis is basically a simple reaction where the temperature is risen to thermally crack and decompose the biomass materials. Pyrolysis reactor. My pyrolysis reactor consists of a dropper with a ball valve, heating chamber where the pyrolysis process will take place, the heating furnace, and also the condenser where all the bio oil are collected. This reactor can conduct pyrolysis up to 700 degrees Celsius. This reactor can do pyrolysis on organic and also polymer-based materials. The organic materials can be either biomass or bio-based materials. This current reactor is using nitrogen as a carrier gas to create inner condition, but later on, other gases can also be fitted into the reactor if needed. Right now, this reactor chamber has a capacity up to 2 liters and can process about 2 kilo amount of materials. The liquid condenser chamber can hold up to 1 liter of bio oil. The reactor is designed so that it can do slow or fast pyrolysis, where both processes are known to produce different amount and different content of the product. To fully utilize the feedstock, all of its product, which is biochar, bio oil and syngas, are tested and confirmed to have its own distinct characteristic as well as value. How the reactor is worked? For this reactor, the procedure are pretty simple. Since the reactor can perform both slow and fast pyrolysis, some additional steps may require to do the fast pyrolysis. First, the sample must be inserted into the reactor. For fast pyrolysis, the sample is filled at the top of the reactor into the dropper, while for slow pyrolysis, the sample can be placed inside the heating chamber directly. Then, nitrogen gas is let to purge the reactor for 5 minutes to remove air and oxygen from the reactor in order to prevent combustion and to create inert condition. Nitrogen is also filled inside the dropper vessel. Then the flow rate of the nitrogen can be adjusted as desired. The reactor temperature is calibrated before and after the sample is placed in the reactor. The temperature of furnace and set point temperature can be set from the control box or control panel. Inside the reactor, we have ice water, which is used to cool the condenser chamber and to collect the bio oil after the volatile gases leave the heating chamber. Enough ice is added to ensure that the condenser is at a low temperature throughout the process until shutdown. The furnace is turned on and reactor is then let to heat up to the desired temperature by adjusting the setting of heating plate and heating chamber. For fast pyrolysis, after the temperature is reached, the ball valve from the dropper is let open to drop feedstock inside the heating chamber. For slow pyrolysis, since the sample is already inside the heating chamber, the pyrolysis already takes place when we heat up the reactor. The pyrolysis is let to run for the whole duration of holding time. The holding time range from 10 minutes to 3 hours. After the holding time has been achieved, the heating plate is shut down and the sample are let to cool until room temperature. After reactor and sample have cooled down, the reactor can be opened and the sample can be removed from the heating chamber for further analysis or usage. For the originality of my innovation, a large amount of biomass feedstock can be processed in one run, as compared to lab-scale reactor, which means larger amount of product can be obtained easily. As mentioned, this reactor can run both slow and fast pyrolysis, as well as can process different types of feedstock, whether it's organic or plastic-based waste. This reactor can also have a slow heating rate, which ensure even heating and thorough reaction throughout the sample. Since different types of feedstock can be processed, this reactor also has the capability to process single or co-pyrolysis, in which different samples are processed together and the reaction between these samples can generate a different outcome. For the applicability, the benefit of this innovation is that it can produce different yield and different composition of product, since it can run both slow and fast pyrolysis, as well as it can process different types of materials. By utilizing the waste as feedstock, this will add worth to any waste materials into value-added good. The obtained product can also be an intermediate materials, which then can be further processed or reformed into other meaningful materials. Another advantages of this innovation is that it simulates the petrochemical processes and able to manufacture products that are similar to that in the industry. Currently, we already published 2 papers in Q2 journal using the reactor. The technology readiness level for the reactor is now at level 6, which is at viability demonstration stage. Patent on this innovation also has been filed and it is pending approval. Commercialization value for this product is related to this innovation has a high potential to explore and widen the fuel, the chemical, the heat and power market, since the generated product can be used in various applications. The bio oil can be a source of organic, phenolic and sugar-based compound. Based on research, the bio oil can be marketed around 32 ringgit per gigajoule, while for the biochar, it can be used as a solid fuel because the char has similar characteristics as coal and commercial charcoal. This product can be also used in co-firing of fuel and upgraded via separation and reforming process. In addition, the biochar can be transformed and utilized as activated carbon in the dye solar cell in the photovoltaic device. The process is costing less money from the feedstock, since it can carry out on waste and also being co-pyrolyzed with other materials. Waste product would require less pretreatment, and this would simplify the process. Due to its capability to do pyrolysis and co-pyrolysis from various feedstock, the supplies of materials can be continuous and consistent, ensuring sustainable operation. That is all from me, and I hope you gain valuable information from my presentation. Thank you very much.